with that, I'm delighted to introduce Nikunj Oza, who's the leader of Data Sciences Group at NASA Ames. Nikunj is also leading an overall NASA project team applying data mining to aviation safety and operations problems. So please join me in welcoming Nikunj. Thank you.
So yeah, thank you very much, and yeah, I'll try not to frighten you. But first, just a little overview of our group. So the group started in 2002, and we have a mix of people, some machine learning background like me, some in data mining, mechanical engineering, people who managed to bring machine learning into their engineering disciplines while they were in getting their education, and then came to us, some software developers, and we work across all of the NASA application areas. There's earth science, space exploration, and what I will mainly talk about today, which is aeronautics. We do some outside funded work as well, but most of our funding, of course, comes from various NASA programs. And we do tend to have a fair number of summer students and even students at other times of year. So I'll just first go through kind of the motivation of why we're doing data mining for aviation. This is probably a crowd where I don't need to really sell that point, but just the same. Then I'll describe a few events that we found, nothing that should be too hair-raising. Then I'll describe a little bit about how we found these different incidents, and then I'll describe what kind of are the class of incidents that we hope to find in the future. We hope that they don't occur at all, but we know they will, and so we, of course, would like to find some of these. So this is just a description of what's called the Next Generation Air Transportation System, or NextGen. The FAA is leading a vision essentially to move towards what is called NextGen. And this really includes monitoring of the entire aviation system. There is, of course, what we would think of like multiple aircraft, and we have airports, but then there are also things maybe many people don't think of. So at the airport itself, there are assets that can have restricted usage, like runways. There are ground-based vehicles, like tugs, luggage carts, catering vehicles, and others. Then there's, of course, there are places like the FAA Tech Center that manage the national airspace, come up with what there are, of course, flight plans, so that's at the level of individual aircraft, but then also deciding, like monitoring the national airspace as a whole, dealing with weather events. If there are too many aircraft that are destined for a given airport, they will issue what are called ground delay programs, where they delay the aircraft that are going to go there. All of that is managed at various levels within the national airspace. And so you can imagine that there can be a pretty large amount of data associated with that. I already described flight plans. There are the flight tracks themselves. There's weather data. There's increased desire to use weather forecast data. So that you can have a little bit more of a predictive capability of what's going to happen on your flight plan in the future. There's thought about even integrating passenger data into that, so that, let's say, if you just want to delay one flight as opposed to another, you can imagine it would make more sense to delay the flight where more of the people have that destination as their endpoint, as opposed to those who are going to use that as a stopover to go someplace else. Now, this describes at a high level the kinds of incidents that we are looking for. And so we assume a structure of this sort where the overwhelming majority of the time, of course, we're operating in a safe state. And when I say we are operating, I'm talking about the national airspace as a whole, or all the way down to an individual aircraft, or different levels that are in between. So we assume we're operating in the safe state, but under some context, there's a greater than desired chance that we may move into what we're calling here a compromised state. Again, the majority of the time we do end up recovering into a safe state, but there's always a chance that things degrade further to the level of what you might call an incident, something where a safety analyst would be a little bit uncomfortable. Again, most likely things do recover into a safe state, but once in a rare while we will end up with an accident. And here, by the way, I'm defining accident as one where you have loss of life or loss of some sort of infrastructure, like let's say the aircraft is a loss, or some other infrastructure gets damaged. Whereas with an incident, there's at least no damage, but at least something happened where you say, okay, it would have been better if that had not happened. So we're really aiming to find sequences like this. Of course, many of these are known, and so exceedance-based methods are most of what are used currently within the industry to find them. So these are known anomalies or safety issues. So for example, there's one what is called a high-speed exceedance that you see up on landing. So this is one where when you're on landing and the altitude is 1,000 feet, if the aircraft speed is greater than 250 knots, we call that a high-speed exceedance. We would like the speed to be less. There's still a pretty low chance of an incident or an accident happening, but this is kind of like violating the speed limit. You'd rather that it not happen. Most of the exceedances are of this form, rules over a handful of variables. And of course, these are great for identifying problems that you know about. There are many problems that people know about, and so they look for them. But almost by definition, this cannot find anything that is unknown. So that's where the thought was, why not use data-driven methods where you really learn the statistical properties of the data and try to find what sort of looks funny. And we assume that this would work well largely because, I mean, as you know, the aviation system overall is overwhelmingly safe. It's to the point where you really cannot just analyze incidents or accidents in order to understand what's happening. You really need to look for these, what you think of as precursors, situations where there's a little bit higher than normal probability that an incident or an accident would happen. So we figure by using data-driven methods, especially data-driven methods for anomaly detection, we can identify what are statistically normal. Almost certainly those are going to also be operationally normal. So we can very quickly then eliminate those from consideration and get down to things that are identified as statistically anomalous, because we figure they're the ones that are going to contain the problems. So certainly, of course, they're going to contain known problems. They don't happen very often, so those known problems are also statistically anomalous. We're especially interested in these unknown problems, but of course there are going to be false alarms. This, by the way, isn't all drawn to scale. This whole set of statistical anomalies is probably like way down here someplace, and the known problems, I'd have to put it in probably less than 1 point font in order to draw it properly. But this essentially describes kind of the lay of the land, right? We want to, of course, as was discussed earlier, we really want to reduce this false alarm rate and want to be able to drill down to these unknown problems very quickly. And so the pipeline that we have used fairly successfully here is to use data-driven methods. Yes, we've had some false alarms, but we've managed to identify some problems that industry has found interesting, and then they have modified their exceedance detection methods, so the set of rules that they use to identify new problems. They typically do not tell us what changes they make because of competition, sensitivities, and the like, but they at least give us a pat on the back every once in a while. So a lot of what I described is anomaly detection over a relatively large set of variables. So this is looking at sequences of flight data where you have a number of variables ranging from something like 150 to 400 or so, and we're trying to find anomalous chunks of that data. But in some cases, we have a particular variable of interest. So for example, we had an internal seedling fund type effort where the idea was to use other variables that are measured on board aircraft to predict fuel burn, in the sense of find what should the fuel burn be given the current way that the aircraft is operating. And we, of course, do know what the instantaneous fuel burn is, and we compare the two. And if the actual fuel burn is significantly greater than what we expect it to be, we can figure, okay, something funny is happening with the aircraft there. Another area we're going into is precursor identification. So this is a case where we're taking, say, a known problem, like the kind of things, something like the high-speed exceedance that I described before, and we're trying to identify what precursors may be happening that may not be contiguous in time, but where you have a higher probability than normal of having that, let's say, high-speed exceedance take place. So we have, for example, with high-speed exceedances found what you can describe as essentially an envelope before that, where you say, okay, even if you're relatively far away from landing, if your overall energy state, like a combination of speed and altitude, is beyond a certain level, there's a pretty high probability that you're going to violate that high-speed exceedance. Or like what I've described here, there's one undesirable effect called go-around. You may have experienced that during landing where looks like you're coming in for landing and then all of a sudden you can feel the aircraft pitch up and you can tell that the engines are being revved up because you hear this ring. So those, of course, are annoying to everybody, right? They annoy the passengers because they delay the flight, and that has a cost to carriers. In fact, on average, go-arounds cost the airline $1 million every time they happen. So they'd like to prevent that if possible. So in this case, we gave we had developed an algorithm in-house where we gave it some examples of go-around, and of course, many flights where go-around did not happen, and it was automatically able to identify potential overtake situations. So this was where an aircraft was going too fast relative to the aircraft in front of it, or may have been approaching at too high speed, and so probably air traffic control directed it to go around for the sake of safety. Another area, I won't end up talking about it here, it's not something we've been able to do a whole lot lately, but that's text mining. So this is mining of aviation safety reports. So there's a system run at NASA Ames called the Aviation Safety Reporting System, where anyone after a commercial flight can report a problem, and then that goes into our system, and it's classified into a set of 60 known event types. So we've been doing some attempts at classifying new reports. It's pretty labor intensive to do this, and of course there are multiple reviewers, and so there's the desire for uniformity. So that's why we were brought in to develop a classifier over these reports. And then we're also interested in doing topic identification. So there are currently, I think, about, over the last 35 years, maybe 800,000 reports that have come in, and so trying to break that up into different topics and then allow for drill down and further analysis. But so really the key for us is, that we have heterogeneous data. I mean, I kind of alluded to the kinds of data we're dealing with. There's, of course, what's going on board. There's the data collected on board. There's radar track data. So you may have seen radar tracks around an airport. There's that kind of thing. I described text data. There's really the desire to mine all of that together to really understand what's going on in the national airspace beyond what is already known by experts in the domain. But these data are quite difficult to deal with. So by the standards of many problems that you all deal with, the volumes are probably not ridiculous. So about 1 year of radar track data is probably about, uncompressed, maybe about 3 terabytes or so. It's not too bad. Adding weather, maybe another 3 terabytes. We have not so far been able to merge that with data collected on board. But, again, it's, some of you are probably laughing that, the amount of data isn't ridiculous. For that matter, the velocity isn't, tremendous either, perhaps. Still in maybe the, hundreds of gigabytes per month, uncompressed, but still maybe halfway manageable. But it's really the other 2 V's where you start running into more difficulty. So veracity is a big problem for us. We do get data dropouts. We get duplicate tracks, data tracks that's where the flight seems to be starting or ending in midair. Not one of your flights, rest assured. They don't correspond to real data, please. But I mean, any kind of problem you can imagine does happen. And I kind of already alluded to the variety of data that we are dealing with. So this is sequential data, discrete and continuous. There's a desire to use voice recordings. We certainly would like to use that. Text reports, weather. So very difficult problem all around to deal with. So I'll describe a little bit now, after having given some motivation about just what are just a few examples of the kinds of problems that we found. I won't go too deep into descriptions of them. But so here's an example where about 30 seconds after takeoff, so this is just showing that what the altitude is for that flight over time, and it's what you would expect to see for a flight that's taking off. Now normally though you would like to see the airspeed go up steadily, but in this case it actually came down for about 30 seconds before finally going up again. Now apparently at this airport drop in airspeed during takeoff happens reasonably frequently, but this particular flight came in as anomalous because the airspeed dropped to within only 12 knots of the expected stalls, of the estimated stall speed. So stall, of course, is a speed at which your aircraft doesn't have lift anymore, and so it just sort of comes down. And so this particular flight came abnormally close to stall speed, and so that's why this flight registered relatively high on the anomaly list. And this was a flight for which the existing exceedance detection methods did not identify anything that was relevant to this particular flight. Now, that what I described is from data that was collected on board the aircraft. This is from radar track data. So in this case, this is from flight over JFK. And what you can, it may be a little hard to see, but you can see there are some flight tracks here in gray that show the typical approaches onto this particular runway. Now, this flight in red was identified as anomalous because of the shape of the trajectory. And in particular, in this case, it's going in for approach, and you can see that it actually overshot the runway, what is called the extended runway center line. It kind of did one of these, I don't know, almost Dukes of Hazzard type turns, I guess. And it just about lined up over the runway here, which was a little bit too close to touchdown. So chances are either it was told or perhaps the pilot decided that they should do a go-around. And so they did a go-around with the idea of trying to land. You may just barely be able to see that the aircraft actually overshot the runway a second time. But this time, luckily, not by very much. So it was actually able to line up and land properly. So this was one where it was just the shape of the trajectory was a bit unusual, and so it was identified as anomalous. And again, no relevant exceedance, so meaning using the known methods was actually identified. So this would have just gone unnoticed if it wasn't for our data-driven methods. Now, this is another case, a recurring high-speed vertical exceedance. And so in particular, so this, it shows actually multiple landings of the same aircraft, of the same flight, I should say. It may have been different aircraft. But it's the same flight. It's a cargo flight that was landing sometime from 11 p.m. to 1 a.m. at JFK. And you can see there's quite a wide variety of landings and a good deal of creativity in the shape of the trajectories here, which you may not normally like to see, I suppose. And so it's this variety of trajectory shapes is what led our algorithms to raise these relatively high on the anomaly list. But this was actually deemed to not really be a safety issue. And the reason is because it was landing at night when there wasn't other traffic around. This was a cargo flight, so passenger comfort is not really an issue. And so actually the air traffic controllers we consulted with thought this was an interesting way of revealing flights that are not following standard operating procedures but are not really safety issues. So when a new controller comes online, he shouldn't see this and raise an alarm needlessly. So that was kind of something unexpected for us, but an interesting way of showing how we can contribute to training. So I described examples of identifying individual anomalies, but here we're really going to precursor identification. So I mentioned here earlier the example of go-around and how in some cases it's high speed on approach that is a precursor to go-around. And this is just an example of a plot showing that here. So this gray band here just shows the 90th percentile of ground speeds that aircraft typically have going in for approach. And this particular one was a little high in its ground speed. Now, I'll just give a brief description of kind of how we found some of these anomalies. So we developed a method in-house called the multiple kernel anomaly detection. It was published in KDD in 2010. Where it's able to use, it uses one-class support vector machines where, I mentioned that we see anomalies as data points that are kind of far away from the rest. Now, how do you measure far away when you have heterogeneous data? You have discrete sequences, continuous sequences, and others. And the way we do it is by using different kernel functions that are appropriate for different modalities. So we have one kernel, a way of measuring similarity over discrete sequences, another over continuous sequences, and then you can have other kernels over other kinds of data. And by combining all of those measures, it's able to find a measure of similarity for every flight with every other flight. And so, of course, those flights that are kind of far away from the rest are revealed in this way. We were able to use the same algorithm, the same core algorithm for the onboard collected data as opposed to the radar track data, but of course we use different kernels. Now, the kinds of precursors we want to find are ones where I've depicted here. We're interested in finding ways of what are the precursors to hazard states. So a hazard state can be, for example, the go-around that I mentioned. So we want to find what is that point at which the probability of heading to that hazard state is noticeably greater than what you would get from taking any other kind of action. So that's essentially what our algorithm finds. One thing that we've informally been able to see that the algorithm finds that we didn't really think of are corrective actions. So what are cases where at first it looked like you were on a track towards that hazard, but somehow a corrective action was taken to lower that probability of going to the hazard again. This needs to be evaluated a little more formally with domain experts, but an informal analysis has shown us that we're able to get that kind of information, and we're actually working right now on a demo of a real-time indication, what we're calling a precursor index, where you can continually monitor and see what is the probability that you're going to get to that kind of an unsafe state, and so you can monitor and maybe take some corrective actions. Now, I won't go into too much depth with this, but the algorithm that we use is, again, an in-house developed one. It's one that's able to use inverse reinforcement learning on the substantial amount of flight data that we have to essentially learn what an expert controller would do, as opposed to what could be done perhaps by, is done by someone who, let's say, ends up reaching the adverse or hazard state. And it's then able to discover the states that or I should say the actions that lead to states that have a much lower value in reinforcement learning terms. And so those end up representing essentially precursors. So for example, choosing to go at a higher speed as compared to a normal speed, that would have a lower value, and hence that would be considered a precursor in the parlance of reinforcement learning. Now, so far as the kind of things that we hope to find coming up, I've really so far described things at a relatively low time scale and also a relatively low spatial extent, right, within the confines of one flight, or maybe just a few minutes of radar track data, so involving a handful of flights. We really want to broaden our time horizon and space horizon, ideally to like months and maybe the national airspace. So one thing we're looking at right now is what happens when there are changes in procedures implemented. Now, procedures are often changed because of some problem that has been shown to pop up, and the thought is that you want to change the procedure in order to reduce the chance that those problems happen again. Now, there's the question, do problems really reduce? Now, you can imagine when a procedure change happens that at first you get a little bit of a spike in problems because there's teething troubles in adopting a new procedure, but do those problems that you wanted to have disappear actually disappear? And do new problems pop up, perhaps? We're hoping we can use our algorithms to help in identifying these kinds of issues, and that's what we're working on right now. Another problem that we have actually is that our algorithm, the MCAT, is able to identify anomalous flights and normal flights, but we're not able to give it domain expert feedback right now. So we're working on, in this case, it's a classifier that essentially takes as input any kind of anomaly that our algorithm finds, allows for subject matter input, and then will, of course, suppress any of the false alarms based on what the subject matter expert says, and raise the profile of those problems that were really deemed to be safety issues by the domain expert. As far as longer term, I think I kind of described the idea of algorithms and tools that really work at multiple time scales and at multiple spatial extents. So of course we need data from all these levels, so all of the 4 V's that I described are only going to get worse for us, but we like challenges. Another thing we're thinking about is the use of distributed privacy-preserving data mining. There are competition sensitivities across air carriers, but there would be value in mining their data jointly. It is currently done as part of an FAA-led effort called Aviation Safety Information Analysis and Sharing, or ASIAS. We love acronyms. But this is one where the mining is done by one trusted broker. Maybe could everybody do their own mining with all that data jointly and not expose other carriers' information? That would be worth exploring. So This is a site we have. It may be a little hard to read, but it's dashlink.ndc.nasa.gov. This is someplace where any of you can sign up and become a member. You can set up a profile like this, preferably with a better looking picture. Describe your interests, upload your publications. If there are any data sets that you're allowed to upload, you can upload those as well. You can set up project pages where you can have discussions on particular topics of interest. This is something that we maintain. I'm hoping we can do something to spruce that up a little more. It's been a little while since we've done that. But it's a community of around 450 or so members right now, people interested in data mining and systems health management. And if you're looking for any bedtime reading or interested in what we're working on, please let me know. Thanks.
Nikunj, thanks. I'm glad we didn't schedule you for the last session of the day. Yeah, safe travels, everyone. Okay, questions. Okay, let's go right to the back of the corner. Who's, sitting down there?
Hello. Is there some notable false negatives that you can share?
Notable false negatives. There's actually none that I can think of right now, and I think part of it is because, admittedly, when we work with domain experts, we go through pretty much in order from most anomalous to least anomalous. And so we, of course, tend to really focus on examining the top so many anomalous flights. It certainly would be a good idea to at least go through some set of the flights that were identified as normal and see if there are any kind of issues associated with that. I'm hoping that the active learning framework that we've set up to gain domain expert feedback may help with a little bit of that. So I'm thinking then that maybe some of the flights that were deemed normal, like I think I described before about some of the flights where there was a drop in airspeed, but they did not show up as very anomalous because they did not get close to stall speed. Maybe in some cases it'd be worth looking a little more closely at those to see if there was maybe really anything going on that's worth learning from.
Can I ask another one? If there's no. Okay, can I ask another one if there's no one?
Hold on. No, let's see. I've got a couple of other hands up. All right. If we've got time and there's no other hands, I'll come back.
Could you go back to your slide with the kernel visualizations? That one. These ones on the right look like T-shirts you can buy on Telegraph.
Ah, yes.
I'm a visualization geek. Can you describe what those are trying to show?
So what this is essentially showing is, so I should say this wasn't designed with a visualization geek in mind. Admittedly, this is maybe more PowerPoint graphics than anything, but so this is really showing it's a kernel function in the sense that every flight is represented in both the row and the column, and you would expect the diagonal should represent maximum similarity. So these are probably I don't know that that's actually true here, but they all should represent similarities of 1 because every flight is maximally similar with itself. And then the other colors should indicate how similar different pairs of flights are. So the idea is that a flight that's very different from most other flights should show up as relatively anomalous. So probably, kind of from looking at the color scheme, probably those flights that have lots of blue in their rows or columns should tend to be more anomalous than those with a lot of red in them. So that's at least the idea behind this.
I'm just thinking if I squint, maybe they'll turn into 3D.
No, yeah, you might hurt yourself trying to squint to look at that one. So, honestly.
Very cool though.
Okay, question right at the back there. Yeah, thanks.
So it's very interesting work what you're doing. I'm wondering how close are we to autonomous flights, and how much of your efforts will apply to that versus really kind of just being for human piloted flights? I mean, is there a point at which you say, okay, enough safety for humans because now we're just going to move on? Now we're just going to be automated in 2 years or 10 years or something.
Yes, so a lot of flight actually is autonomous already. So cruise, cruise largely is, but And chunks of takeoff and landing are still done in at least with some manual intervention. I think overall at least personally, I think there are always still going to be humans in the loop at some level, constantly monitoring things. And I think another issue with this is that we're probably never going to get to a point where we can switch the entire national airspace over to a totally autonomous system. It's going to be a natural transition, and we don't know all of the problems that are going to pop up as parts change. So there's always going to be the need for some of this kind of monitoring.
Or till Elon decides to get into this. Or till Elon Musk decides to get into this.
Do you want to give us your second question? You're right there.
So how much data do you match it against, both temporally and as in geographically around the station?
So we right now are focused mainly on takeoffs and landings because that's where the most difficulties tend to take place. So this tends to be from the touchdown point going out most typically about 30 nautical miles, sometimes a little bit more. And so what's that, something like 5-10 minutes worth of data per flight. And then as far as number of flights, it varies a bit. We do tend to have separate models on a per runway per month basis, just to have a proper apples to apples comparison for everything. So typically we don't end up having more than, say, maybe I have a few thousand flights that are in any given run of MCAD.
Okay.
So, but of course we then have the multiple models and are checking all of those then for anomalies.
Thanks.
Good. Okay, time for one more question. So right at the front here. Oh, can you wait for the microphone? Thank you.
Short question. So just to be clear, you're talking about both ATC as well as the flight, rather the pilots complying with the instructions and trying to find out the exceedance, etc. So this basically detects only from the aviation point of view or from the ATC, air traffic control point of view too?
So we are working on both, but as separate problems. We so far have not been able to merge the onboard collected data with air traffic control, so the radar track data. So with radar track data, we have multiple flights, but they essentially are treated as dots moving around in the space. We don't end up having information on what's going on board. As opposed to then for the flight data, what's collected on board, it's purely what is happening with that flight on board. We do have position information, but then we don't necessarily know where other flights are.
Because a lot of these anomalies in takeoff and landing take place when the interaction between the air traffic control as well as the pilot. So that, for example, run around, etc. If they're coming in very fast, even though they were instructed to come slower or designated speed. So that's interaction of the two factors which are treated independently. That's what you're saying?
Yeah, and also we so far have not been able to make much use of things like voice data. So in many cases we're really taking educated guesses about what must have happened between air traffic control and the crew on board, where maybe one of them directed a go around to take place.
Okay. Right. Yeah. Nikunj, thanks so much for your time.
Thank you.